The name of the module is Fisher-Neyman factorization theorem. In the last module, we have discussed the concept of sufficient statistic. We have seen that a statistic capital T will be sufficient for a parameter theta if the conditional distribution of the whole observation x given T is independent of theta. Now, in any problem there are infinitely many statistics, and to determine a sufficient statistic for a parameter theta, it is not possible to derive the conditional distribution of x given the statistics. So, in this module we are going to discuss a method for deriving a sufficient statistic. This is called Fisher-Neyman factorization theorem. It helps us to determine whether a statistic is sufficient or not. Some examples will be discussed in this connection. Our objectives are to introduce a technique of determining sufficient statistics for a family of distributions. The technique is known as the Fisher-Neyman factorization theorem, and to illustrate the use of the factorization theorem through examples. Let x equals to x1, x2, xn be a random sample, taking values in the set script x, which is a subset of r to the power n. Consider a statistic capital T, which is a function of x, such that the conditional distribution of x given t equals to small t is independent of theta for all possible realizations small t of t. Then t will be called a sufficient statistic for theta, or it is sufficient for the family of distributions indexed by theta. But in any problem there exist infinitely many statistics, virtually any function of the sample that is free of the parameter, and it is a difficult task to ascertain which of these is sufficient for the parameter. In the present module we discuss a very simple technique for determining sufficient statistics. This method originally due to Fisher and Neyman. It is later generalized by Helmholtz and Savage, and the method is known as Fisher-Neyman factorization theorem. Let us state the theorem. Let x1, x2, xn be an n-dimensional random variable with PMF or PDF given by small f theta x1, x2, xn, where theta belonging to script theta, here theta may be a vector valued or real valued parameter. A statistic capital T is sufficient for theta if and only if small f theta x1, x2, xn can be factorized as f theta x1, x2, xn is equals to g theta t into hx, where g theta t depends on theta and on x1, x2, xn only through t, and h x1, x2, xn is independent of theta. For the sake of simplicity, we prove the theorem only in the case of discrete distributions. Let us write x as x1, x2, xn and small x as small x1, x2, xn as a realized value of x. First we prove the only if part, that is the necessary part. Suppose t is sufficient for theta. If tx equals to t, then it can be say that x equals to x implies tx equals to t, and hence x equals to x is a subset of tx equals to t, and we can write f theta x is equals to probability under theta x equals to x, and this is actually probability under theta x equals to x intersection t equals to t. This is so because x equals to x is a subset of t equals to t. This can be written as probability under theta t equals to t into probability x equals to x given t equals to t, provided the conditional probability is well defined. As t is sufficient for theta, the conditional probability x equals to x given t equals to t is free of theta, and we write as hx equals to probability x equals to x given t equals to t. Now, if we write g theta t as probability under theta t equals to t, that is the marginal distribution of t, then we get the required factorization. Now, we are going to prove the if part of the theorem. Suppose that the factorization holds, then for any fixed value small t, we have probability under theta t equals to t. This is equals to summation over those small x for which tx equal to t, and in the summation that this is the probability x equals to x, that is we take summation over probability x equals to x and the summation is taken over set of all x for which tx equal to t. Now, probability x equals to x can be written as g theta tx into hx because here the factorization holds, and hence we get g theta t into summation over x such that tx equal to t in hx. If t satisfies probability under theta t equals to small t greater than 0, then we get the conditional distribution as probability x equals to x given t equals to t is equals to probability under theta x equals to x comma t equals to t divided by probability under theta t equals to t, and the numerator is actually equals to probability under theta x equals to x because x equals to x implies t equal to t, and it is valid when the observed value of capital T is small t, and therefore we get the conditional distribution as probability under theta x equals to x divided by probability under theta t equals to t, which is equals to g theta t into hx divided by g theta t into summation over x such that t equals to t hx. After cancelling the factor g theta t, we get finally hx divided by summation over x tx equals to t hx, and it is independent of theta, and therefore we see that the conditional distribution of x given t is independent of theta, therefore t is sufficient for theta. Now we make some important remarks. Remark 1. If t is sufficient for theta and t star equals to some function of t, here we write t star equal to phi t, where phi is some one-to-one function, then t star is also sufficient for theta. To justify the statement, since phi is one-to-one, we can write t equals to phi inverse t star. Since in case of a one-to-one function, inverse function exists, hence by the factorization theorem, f theta x equals to g theta t into hx, we write in place of t we write phi inverse tx and we get g theta phi inverse tx hx, and here we can write this as g star theta of t star x into hx, where g star theta is the function of the function g of phi inverse. Now, using the sufficiency part of the factorization theorem, we see that the function t star is sufficient for theta. Just any function of a sufficient statistic is not necessarily sufficient, as the following example shows. Let x be a single observation from normal distribution with mean theta and SD1. Here theta is the unknown parameter. Application of factorization theorem on the normal density, it is very easy to show that x is sufficient for theta. But x square is not. And it is to be noted that x square is a 2-to-1 function. While not directly relevant to the point in hand, we state here that x is not sufficient for theta square. It is very clear because theta square takes only positive values, but x takes both positive and negative values. We consider our second remark. A necessary and sufficient condition for a statistic capital T to be sufficient for a parameter theta is that for any fixed theta 1, theta 2 belongs to script theta, the ratio f theta 1 x divided by f theta 2 x, this is the ratio of the PMF or PDF at the 2 points theta 1 and theta 2. It is a function of the observed sample x only through Tx. To justify this statement, it is clear that it is directly follow from the factorization theorem. Our third remark is, if T1 and T2 are two distinct sufficient statistics for theta, then T1 is a function of T2. But if T1, T2 is jointly sufficient for theta 1, theta 2, then it does not follow that Tj alone is sufficient for theta j, j equals to 1, 2. Now we make a very important observation. Let x1, x2, xn be a random sample of size n drawn from a continuous distribution with PDF f theta x. Then the order statistics, that is the set x ordered 1 to up to x ordered n, are jointly sufficient for theta. To justify this statement, the PDF of x1, x2, xn can be written as some g theta x1, x2, xn equals to n factorial into product j from 1 to n f theta x ordered j, f theta xj, and thus we get the joint PDF of x ordered 1 to x ordered n as g theta x ordered 1 up to x ordered n is equals to n factorial into product over j from 1 to n f theta xj. Note that product over j from 1 to n f theta xj is the joint PDF of xj's, and therefore we get product over j from 1 to n f theta xj is equals to g theta x ordered 1 up to x ordered n into 1 by n factorial. Clearly, the joint density of xj's has been factorized such that the former term depends only on the ordered sample and the parameter theta, and the latter is independent of theta. Hence, x ordered 1 up to x ordered n is sufficient for theta. This result is very useful when there is no single sufficient statistic for theta. For example, in case of Cauchy theta, 1 population, there is no single sufficient statistic, and here we use the whole set of order statistics x ordered 1 to x ordered n as a sufficient statistic for theta. Now we consider some examples. In our first example, we consider a set of n independent Bernoulli trials with probability of success p per trial. With the jth trial, we associate the random variable xj equals to 1 if the trial results in a success, equals to 0 otherwise. Then the PMF of each xj is given by bpx equals to p to the power x into 1 minus p whole to the power 1 minus x if x equals to 0, 1, 0 otherwise. The joint PMF of x1, x2, xn is given by fp x1, x2, xn. This is equals to p to the power summation over j from 1 to n xj into 1 minus p to the power n minus summation over j from 1 to n xj if each xi can take the value 0 and 1. Now this can be written as a function gp of summation xj into h x1, x2, xn, where now if we set t equals to the summation x1, the summation over j from 1 to n xj, then we get gp of t is equals to p to the power t into 1 minus p to the power n minus t if t from 0 to n 0 otherwise, and h equals to 1. Hence we see that the joint PMF of x1, x2, xn is factorized into two parts. The first part gpt, here it depends on the parameter t and the original observations x1, x2, xn through the statistic t, and the second part h x1, x2, xn is independent of the parameter. Hence the summation j from 1 to n xj, which is the total number of successes in all n trials, is sufficient for the parameter p. We consider our second example. Let x1, x2, xn be n independent observations from a normal distribution with mean mu and variance sigma square. Here mu is unknown and sigma square is known. Then the PDF of each xi is given by 1 by root 2 pi sigma square into e to the power minus 1 by 2 sigma square x minus mu whole square. The joint density of x1, x2, xn is given by f mu x1, x2, xn. This is product over j from 1 to n, the marginal PDF of xj, and it boils down to 1 by sigma root 2 pi whole to the power n into e to the power minus 1 by 2 sigma square into summation over j from 1 to n xj minus mu whole square, where each xi belonging to real line. Now the joint density can be factorized as 1 by sigma root 2 pi to the power n into e to the power minus 1 by 2 sigma square into summation over j from 1 to n xj minus mu whole square. If we adjust xj minus x bar plus x bar minus mu, then we get e to the power minus n by 2 sigma square x bar minus mu whole square into e to the power minus 1 by 2 sigma square summation j from 1 to n xj minus x bar whole square into 1 by sigma root 2 pi to the power n. Now the first part can be written as a function of x bar. We write it as g mu x bar, and the second part, which is independent of mu, we write it as h of x1, x2, xn. If we write t equals to x bar, then we get g mu t is equals to e to the power minus n by 2 sigma square into t minus mu whole square. Note that g mu t depends on the unknown parameter mu and the original observations x1, x2, xn only through t, and we write h x1, x2, xn as e to the power minus 1 by 2 sigma square summation j from 1 to n xj minus x bar square divided by sigma root 2 pi to the power n. hx is independent of the unknown parameter mu, and hence by factorization theorem x bar, which is 1 by n summation over j from 1 to n xj, is sufficient for mu when sigma square is known. Next we consider an example where x1, x2, xn are independent observations from a Poisson distribution with mean lambda where lambda is unknown. Then each xj has PMF e to the power minus lambda into lambda to the power x by x factorial if x equals to 0, 1, 2 dot 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 0 otherwise. The joint PMF of x1 x2 xn is f lambda x1 x2 xn is equals to product over j from 1 to n p lambda xj. This is equals to e to the power minus lambda into lambda to the power x1 plus x2 plus xn divided by product over j from 1 to n xj factorial if each xi can take the values 0, 1, 2 dot 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 and is 0 otherwise. Now the joint PMF can be factorized as f lambda x1 x2 xn is equals to e to the power minus n lambda into lambda to the power summation j from 1 to n xj divided by product j from 1 to n xj factorial. The first part can be written as a function of summation xj and we write this as g lambda summation xj, and the second part is independent of lambda and we write it as h of x1 x2 xn. Now if we set t equals to summation j from 1 to n xj, then the first part can be written as a function of t, it is g lambda t. G lambda t is equals to e to the power minus n lambda into lambda to the power t, and the second part is independent of lambda and this is actually 1 by product over j from 1 to n xj, and hence summation over j from 1 to n xj or equivalently x bar, actually x bar is a one-to-one function of summation over j from 1 to n xj, is sufficient for lambda. We consider our next example. Let x1, x2, xn be independently and identically distributed random variable, each follows uniform distribution with parameters 0 and theta. Then each xj has PDF u theta x equals to 1 by theta if 0 less than equals to x less than equal to theta. We write here as the indicator function 1a as the indicator of the set A. Then the joint PDF of x1, x2, xn is given by f theta x1, x2, xn is equals to product over j from 1 to n u theta xj, and this is actually 1 by theta to the power n into I into 1 of x order n. Here it is 1 0 theta x order n is equals to 1 if x order n lying between 0 and theta, 0 otherwise. Here x order n is the maximum of x1, x2, xn. Therefore, the joint PDF can be written as f theta x1, x2, xn is equals to 1 by theta to the power n into the indicator function 1 0 theta x order n. The first part that means 1 by theta to the power n and 1 0 theta x order n can be written as a function of x order n. We write it as g theta x order n. Therefore, if we set t equals to x order n, then we get g theta t equals to 1 by theta to the power n into the indicator 1 0 theta t, and here we take h x1 x2 xn is equals to 1. Hence x ordered n, which is maximum of x1 x2 xn, is sufficient for theta. We consider our next example. Let x1 x2 xn be n independent observations from a normal distribution with mean mu and variance sigma square. Here both mean and variance are unknown. Then each xj has PDF some n mu sigma square x is equals to 1 by root 2 pi sigma square into e to the power minus 1 by 2 sigma square x minus mu whole square, where x belonging to R real line. The joint density of x1 x2 xn is given by small f x1 x2 xn is equals to 1 by root 2 pi sigma square whole to the power n into e to the power minus 1 by 2 sigma square into summation over j from 1 to n xj minus mu whole square. Here each xi belonging to R. Now the joint density can be factorized as f x1 x2 xn is equals to sigma square to the power minus n by 2 into e to the power minus n by 2 sigma square into summation j from 1 to n xj square plus mu by sigma square into summation j from 1 to n xj minus n mu divided by 2 sigma square into root 2 pi whole to the power minus n. Now the first part is a function of the two statistics, summation j from 1 to n xj square and summation j from 1 to n xj. We write is as a function of summation j from 1 to n xj and summation j from 1 to n xj square. If we set T1 equals to summation j from 1 to n xj square and T2 equals to summation j from 1 to n xj, then the first part can be written as a function of T1 and T2, and this is actually T1 T2 equals to e to the power minus n by 2 sigma square T2 plus mu by sigma square T1 minus n mu by 2 sigma square whole divided by sigma square to the power n by 2, and we write as h x1 x2 xn equals to 1 by root 2 pi to the power n, and therefore we have to see that summation j from 1 to n xj and summation j from 1 to n xj square is sufficient for mu sigma square. Here two unknown parameters mu and sigma square, and there are two statistics, summation j from 1 to n xj and summation j from 1 to n xj square. Actually here another sufficient statistics for mu sigma square is x bar and s square, where x bar equals to 1 by n summation xj and s square equals to 1 by n summation j from 1 to n xj minus x bar square. Consider our last example. Suppose x1, x2, xn are independently and identically distributed random variable, each follows rectangular distribution with parameter theta and theta plus 1. Then each xj has PDF u theta x equals to 1 if theta less than equals to x less than equal to theta plus 1. We write it again as 1 theta theta plus 1 x, where 1 a denotes the indicator of the set A. Then the joint PDF of x1 x2 xn is f theta x1 x2 xn equals to product over j from 1 to n u theta xj. This is actually the product of two indicator functions. One is 1 theta infinity x ordered 1 and the other is minus infinity theta plus 1 x ordered n. Here x ordered n is the maximum of x1 x2 xn and x ordered 1 is the minimum of x1 x2 xn. It is very clear that if all observations xi is less than equal to theta plus 1, then maximum of x1 x2 xn is less than equal to theta plus 1, and if all observations xi's are greater than theta, then the minimum will be greater than theta. Hence, by factorization theorem, x ordered 1 and x ordered n is jointly sufficient for theta. In this example, we see that there is only a single parameter theta, but here there are jointly sufficient statistics x ordered 1 and x ordered n, which is sufficient for theta. In the present lecture, what we have seen that the Fisher-Neyman factorization theorem is very helpful in determining whether a statistic is sufficient or not. It tells us if a statistic T is sufficient for theta, then the joint PMF or PDF can be factorized in two parts. The first part depends on theta and on the observation x only through T, and the second part will be independent of theta. Another important fact that we have observed that there is no relationship between the number of unknown parameter and the number of sufficient statistics. The number of sufficient statistics may be equals to or it may be greater than or less than the number of unknown parameters.